Hi folks, in this video we're going to have a look at a question involving lenses and how we can apply that to defects of vision. So in the question we have that a certain student requires spectacles in order to see a book clearly at a normal reading distance. Part A is asking what defect of vision to the spectacle lens is correct, and part B is asking what's the normal cause of this defect. So the person here needs glasses in order to see a book which is close up. So they're not able to see things that are near, but they can see things that are far. So we would describe this person as being far-sighted. They can see things far off, but they can't see them when they're near. And the proper term that we want to use for this is hypermetropia. So when a person suffers with hypermetropia, they're able to see clearly objects that are in the distance, but they're not able to see clearly objects that are close up in front of them. They're not able to form a sharp image on the back of the retina. And in fact, the image would actually be formed behind the retina. So some reasons for this would be that the eyeball itself is too short. So we can see from the diagram that if the eyeball was a little bit longer, then the image would form on the back of the retina. Or maybe the cornea isn't curved enough in order to cause enough refraction for the rays of light to bend enough and meet on the retina. Or that the lens itself is too weak. So again, not powerful enough to refract the light in order to make it meet on the back of the retina. Part C. Without spectacles, the student cannot see clearly objects that are nearer than 80 centimeters from the eye. Calculate the power of the spectacle lens required to reduce this distance to the normal near point of a distance of 25 centimeters. So you would be expected to know that the normal near point of the eye would be 25 centimeters, and the normal far point, that being the furthest that a clear image can be seen, would be infinity. This person, however, cannot see anything closer than 80 centimeters, so their near point is 80 centimeters rather than 25. So to correct this type of vision defect, we would need to have a converging lens or a convex lens. And the reason we need that is because when we place a converging lens in front of the eye, that will start to bring the rays together so that they can meet on the retina. So you should know that for hypermetropia, we would need a converging lens to correct that vision. And if we have a converging lens, that means that the focal length of the lens will have a positive value. If, however, the person had myopia, they were short-sighted, then they would need a diverging lens, and the focal length of that would be negative. And it's important that you understand which type of lens is required to correct which defect, so that you put the correct values then into any calculations. So we want to figure out what the power of the lens is. And to calculate power, we can use the equation P is equal to 1 over F. However, we don't actually have the focal length yet, so we're going to need to work that out. And we can do that using the lens equation, where 1 over F is equal to 1 over U plus 1 over V. So here we're placing an object at 25 centimeters. So the object distance is 25, and that's a positive value. We want to make that object appear as if it's coming from the person's actual near point, which is at 80 centimeters. Essentially what we're trying to do is to trick the eye into believing that an object that is at 25 centimeters is actually at 80 centimeters. And that's because the eye can clearly see an object at 80 centimeters without any need for glasses. So the image distance is being formed at 80 centimeters. And it is a virtual image. That image is formed on the same side of the lens as the object, so therefore that value is going to be a negative value. So we have minus 1 over 80, where 80 is the image distance. And that is at the person's actual near point. So next we'll take a common denominator, which in this case would be 400. And we have 1 over 25, which would be the same as 16 over 400, minus 1 over 80, which would be the same as 5 over 400. So we're saying here that 1 over f is equal to 11 over 400. And therefore f is equal to 400 over 11, which gives us an answer of 36.36. So we'll round that to 36.4 centimetres. Now we want to work out the power of the lens, where the power is 1 over f, but f must be in metres. So power is equal to 1 over f, which we'll write as 1 over 0.364, just so we can keep that in metres, and that will give us an answer of 2.75, and the unit for that then is the diopter. So 2.75 diopters, or 2.75 metres to the minus 1. Now that is a positive value, which is what we would expect for a converging lens. Okay, part D. Without spectacles, the student's far point distance has the normal value. So it hasn't quoted this normal value in the question, but you would be expected to know that, and that normal value is at infinity. So first part is calculate the distance of the student's far point from the eye when the spectacles in part C are worn. So what we're trying to do here is to figure out where would an object have to be placed in order for it to create an image at the person's actual far point, which in this case is infinity. So if we start off by writing out the lens equation, we have 1 over f is equal to 1 over u plus 1 over v. 1 over f, we already know f, we worked it out in the previous question. We had 36.4 centimetres, and that was a positive value of 36.4. That's equal to 1 over u, which is the object distance. That's what we're trying to figure out. We want to know what is the furthest that an object can be where the person is wearing these spectacles that they can still see them clearly. So I'm going to leave that as 1 over u. That's what we're trying to determine. Then we have plus 1 over v, where this is the image distance. So the image in this case is going to appear at the person's actual far point. So the unaided far point, what they can see without the spectacles on. Now that far point is at infinity. So what we have here is 1 over infinity. And that should be a minus as well, because it is a virtual image. Now this 1 over infinity actually turns out to be equal to 0. So what we're finding here is that 1 over 36.4 is equal to 1 over u, which means that the object distance, the furthest object that they can see while wearing the glasses that would create an image that appears as if it's coming from infinity, would be at 36.4 centimetres. So while wearing that glasses, we've determined already that the nearest thing they can see would be 25 centimetres, and the furthest thing they can see would be at 36.4 centimetres. So anything beyond 36.4 centimetres, the student would need to take off those glasses in order to see them clearly. Part 2 of this question says, when wearing the spectacles in C, the student looks at a road sign which is 5 metres away. Comment briefly on the appearance of the sign to the student. Well, as we've just worked out, when the student is wearing the glasses, they can see clearly objects between 25 centimetres and 36.4 centimetres. So since the sign is greater than 36.4 centimetres, it's at 5 metres away, that means that sign will not be in focus. It will not be a clear, sharp image. So when they look at the sign will be blurry. If they want to look at it clearly, they would need to remove the glasses.